Autumn 1940. Above the embattled fields of Kent, the guttural roar of a Messerschmitt Bf 109's Daimler-Benz DB601 engine echoed through the thin air, pursued relentlessly by the iconic thrum of a Supermarine Spitfire's Rolls-Royce Merlin. Squadron Leader Thompson, a veteran of countless engagements, gripped his controls, his eyes fixed on the fleeting German fighter. The Bf 109, a cunning adversary, executed a violent evasive maneuver, banking sharply into a steep inverted dive. Thompson, intent on maintaining the tactical advantage, mirrored the move, pushing his stick forward hard into a decisive negative G pushover. The world inverted. And then, silence. The Merlin engine, usually a symphony of raw power, choked. Fuel starvation, instantaneous and absolute, seized the heart of his aircraft. The sudden, terrifying quiet was more jarring than any flak burst. Thompson wrestled with the controls, frantically attempting to coax life back into the dead engine, but the propeller remained a silent, windmilling testament to his aircraft's fatal seizure. The ground rushed up with horrifying speed. This was not the consequence of a precise burst from a German cannon, nor a lucky strike from anti-aircraft fire. This was an internal betrayal, a systemic, design-intrinsic flaw that had claimed yet another pilot. The Spitfire, a symbol of British defiance, plunged into the earth, a smoking crater marking the end of a valiant fight. This was the silent killer stalking RAF pilots, a deadly operational ceiling imposed not by the enemy, but by their own machines. Yet, this devastating operational flaw was not born of a mediocre power plant, quite the contrary. At the very heart of Britain's aerial defense, powering the legendary Spitfire and the formidable Hawker Hurricane, lay the Rolls-Royce Merlin engine, a marvel of early 20th century engineering that would define air supremacy for a generation. This magnificent 27-liter liquid-cooled V12 was an absolute powerhouse, delivering up to 1,470 horsepower in its later variants. Its raw thrust enabled the Spitfire's iconic climb rate and the Hurricane's robust combat endurance, making them formidable interceptors against the Luftwaffe's technologically advanced platforms. The Merlin was more than just an engine. It was a strategic asset, the very pulse of the Royal Air Force's offensive and defensive capabilities, revered for its reliability and sheer power output. However, this titan of propulsion harbored a critical design element that would prove to be its Achilles heel in specific combat scenarios: its float-type carburetor. Unlike later fuel injection systems, the Merlin's carburetor relied on a simple float chamber to maintain a consistent fuel level, drawing fuel into the airstream through Venturi effect. This precision system was crucial for mixing fuel and air in the exact ratios required for optimal combustion. While highly effective under normal flight conditions, ensuring a consistent fuel-air mixture, this conventional design carried an inherent, yet initially unappreciated, vulnerability to the extreme gravitational forces encountered during aggressive aerial maneuvering. This elegant, powerful, and utterly vital component was, paradoxically, the source of the RAF's gravest combat limitation. In the brutal aerial ballet of World War II, where fractions of a second often dictated survival, a critical tactical asymmetry emerged, gifting the Luftwaffe a distinct and often fatal advantage. This stemmed directly from the engine technology underlying the iconic fighters of both sides. When an RAF pilot, pressed by a pursuing Messerschmitt or seeking to gain a superior attacking position, executed a negative G maneuver, aggressively pushing the control stick forward to dive sharply or change direction, their Merlin engine would falter. This maneuver, a fundamental component of evasive and offensive aerial combat, was intended to exploit gravity, allowing a rapid change in altitude or vector to either escape a tracer stream or surprise an opponent. However, the British Rolls-Royce Merlin engines, powering the Spitfires and Hurricanes, relied on a float-type carburetor system. Under negative G-forces, this system would starve the engine of fuel. The float, designed to regulate fuel flow under normal gravitational conditions, would lift, causing the fuel mixture to become overly lean, leading to a momentary but critical engine cutout. The propulsive power would vanish, often for several terrifying seconds, leaving the aircraft vulnerable, a dead weight in the sky. In stark contrast, the German Messerschmitt Bf-109s were equipped with Daimler-Benz engines featuring direct fuel injection. This sophisticated system delivered fuel directly into the combustion chambers, unaffected by gravitational shifts. German pilots could execute negative G maneuvers, often referred to as bunting, with absolute impunity, their engines roaring consistently throughout. This seemingly subtle engineering difference translated into a profound tactical asymmetry. A Bf-109 pilot under fire could suddenly push the stick forward, drop away, and escape a pursuer, while the RAF pilot, attempting the same, would see their engine momentarily die, becoming a sitting duck. Conversely, a German fighter could suddenly dive to gain speed or reposition for an attack, confident in their engine's unwavering performance. This critical flaw was not merely an inconvenience, it was a deadly operational handicap for the Royal Air Force. It dictated combat tactics, forcing RAF pilots to avoid certain maneuvers that were tactically advantageous but mechanically suicidal. This restriction eroded their combat flexibility and denied them critical escape and attack vectors. The strategic ramifications were significant, contributing to avoidable aircraft losses and, more tragically, pilot casualties. The psychological toll on RAF pilots was immense. They were keenly aware of this inherent disadvantage, flying into battle knowing their German adversaries possessed a mechanical superiority in fundamental dogfighting maneuvers. It was a problem that Rolls-Royce recognized as paramount, yet a solution remained stubbornly out of reach as the urgency of war mounted with each passing day. The root of this critical tactical disparity lay deep within the very heart of the Merlin engine itself, its float-type carburetor. This device, standard for many aircraft engines of the era, relied on a simple yet ultimately vulnerable principle. Fuel would flow into a chamber, and a float, much like in a toilet cistern, would rise or fall with the fuel level, regulating a needle valve to maintain a consistent supply. Under normal positive G forces, or even during slight negative G maneuvers, this system functioned adequately, ensuring a steady stream of aviation fuel to the combustion chambers. However, the aggressive, violent aerobatics of aerial combat introduced an unforeseen variable, sustained negative G. When a pilot executed a sharp, forward dive or pushed the stick violently forward to disengage from a pursuing adversary, the aircraft experienced significant negative G-forces. In these moments, the very principle upon which the carburetor was designed, gravity, was inverted. The fuel, instead of being drawn downwards into the engine, would effectively float upwards, away from the intake. Critically, the float, subject to these inverted forces, would rise to the top of its chamber, mirroring a full fuel tank. This action would then cause the needle valve to close, completely shutting off the fuel supply to the engine. The root of this critical tactical disparity lay deep within the very heart of the Merlin engine itself, its float-type carburetor. This device, standard for many aircraft engines of the era, relied on a simple yet ultimately vulnerable principle. Fuel would flow into a chamber, and a float, much like in a toilet cistern, would rise or fall with the fuel level, regulating a needle valve to maintain a consistent supply. Under normal positive G forces, or even during slight negative G maneuvers, this system functioned adequately, ensuring a steady stream of aviation fuel to the combustion chambers. However, the aggressive, violent aerobatics of aerial combat introduced an unforeseen variable, sustained negative G. When a pilot executed a sharp forward dive or pushed the stick violently forward to disengage from a pursuing adversary, the aircraft experienced significant negative G-forces. In these moments, the very principle upon which the carburetor was designed, gravity, was inverted. The fuel, instead of being drawn downwards into the engine, would effectively float upwards, away from the intake. Critically, the float itself, now subject to these inverted forces, would rise to the top of its chamber, mirroring a full fuel tank. This action would then cause the needle valve to close, completely shutting off the fuel supply to the engine. The mighty Merlin engine, moments ago a roaring inferno of power, would starve, cough, and then fall utterly silent. In the unforgiving crucible of a dogfight, where every second equated to life or death, this engine cutout rendered the Spitfire or Hurricane utterly defenseless, transforming a swift, agile fighter into a vulnerable glider for precious seconds. This was not a manufacturing defect, but a fundamental design challenge inherent in the existing carburetor technology of the time, a technological limitation that Rolls-Royce engineers grappled with, knowing full well the dire consequences it imposed on their pilots in the skies above the Channel. The grim statistics of lost pilots and downed aircraft painted a stark picture, a critical operational disadvantage that Rolls-Royce, the very architects of the Merlin engine, was acutely aware of. Their engineering divisions, renowned globally for their meticulous design and relentless pursuit of perfection, were already mobilized. Teams of the finest minds in aeronautical propulsion were dedicated to eradicating this lethal flaw. However, the institutional methodology of Rolls-Royce, while ultimately leading to unparalleled performance, was inherently geared towards comprehensive, long-term solutions. Their initial thrust involved the sophisticated redesign of the fuel delivery system, specifically the development of a pressure carburetor. This advanced system, unlike the conventional float-type carburetor, would maintain a constant fuel pressure regardless of aircraft attitude or G-forces, thereby eliminating fuel starvation during negative G maneuvers. Such a solution, while elegant in its engineering foresight, demanded a protracted development cycle. It required extensive research, prototype fabrication, rigorous bench testing, and ultimately flight certification, a process that could span months, if not years. Yet the war in the skies above Britain offered no such luxury. Every week lost in development translated directly into more lost Spitfires and Hurricanes, more fallen pilots, and an escalating strategic vulnerability against the Luftwaffe's agile Messerschmitt Bf-109s. This inherent clash between Rolls-Royce's meticulous engineering-first orthodoxy and the brutal, immediate demands of aerial combat created an almost insurmountable paradox. The theoretical paradox of engineering perfection versus battlefield pragmatism was brutally resolved in the skies above England and the Channel. For RAF pilots, especially those flying the Spitfire and Hurricane, the engine cutout during negative G maneuvers was not an abstract technical flaw, it was a death sentence. Reports from squadrons, grimly compiled by Fighter Command, detailed an escalating pattern of catastrophic engine failures following evasive actions or aggressive dives. These weren't mechanical failures in the traditional sense, but rather the instantaneous starvation of fuel to the Merlin engine when gravity reversed its pull, a phenomenon the carburetor was simply not designed to overcome. The human cost was immediate and devastating. Pilots, whose training represented an immense investment of wartime resources, were being lost not to enemy fire, but to a fundamental design limitation. Squadron leaders reported pilots simply falling out of the sky after attempting a maneuver that their German adversaries could execute with impunity. The psychological toll on the remaining air crews was immense. Every dogfight became a gamble not just against the Luftwaffe's superior tactics, but against their own aircraft's inherent flaw. Anecdotal accounts, later substantiated by post-action reports, spoke of pilots making the ultimate sacrifice, not in a blaze of glory, but often in a silent, uncontrolled dive, the Merlin engine refusing to restart. During the critical phases of the Battle of Britain in late 1940 and the subsequent Channel Dash and offensive sweeps of 1941, this vulnerability translated directly into a tactical disadvantage. German Messerschmitt Bf-109s, equipped with fuel-injected Daimler-Benz engines, could dive away or pull negative G evasions with confidence, often escaping pursuing Spitfires or Hurricanes whose pilots were forced to choose between breaking off pursuit or risking a fatal engine cutout. The RAF's attrition rate, already high, was exacerbated by these preventable losses, impacting operational readiness and severely hampering offensive capabilities. The need for an immediate, deployable solution transcended mere engineering preference. It became a matter of national survival, a desperate plea echoing from every combat airfield. The grim tally of fallen pilots and lost aircraft was not merely an operational statistic. It represented a rapidly escalating strategic vulnerability for the Royal Air Force. Luftwaffe pilots, particularly those operating the agile Messerschmitt Bf-109, quickly identified and ruthlessly exploited this critical flaw in the Merlin engine's fuel system.
During the cut and thrust of aerial combat, a sudden negative G maneuver, a bunt or a rapid dive, was a common evasive tactic. Yet, for a Spitfire or Hurricane pilot, this maneuver carried a lethal gamble. The engine would starve of fuel, cutting out for precious seconds, turning the hunter into the hunted, and often sealing their fate. The Air Ministry's communiques to Derby grew increasingly terse, bordering on philippic. The tactical reports from Fighter Command were unambiguous. The RAF was bleeding pilots and surrendering valuable air superiority in critical sectors due to this persistent Achilles heel. While Rolls-Royce's engineers were indeed diligently developing the sophisticated pressure carburetor, a long-term, elegant engineering overhaul designed to rectify the issue permanently, it was a solution many months, if not years, away from widespread deployment. This complex system was a logistical nightmare for immediate implementation across the entire fighter fleet, requiring significant retooling and installation time. The strategic imperative was immediate. The exigency of the air war demanded a rapid deployment solution, a stopgap measure that could be fitted yesterday, not in the distant future. The pressure on Rolls-Royce was immense, with the very balance of air power over the Channel and the British Isles hanging in the balance. While the RAF's frontline pilots grappled with the deadly G-cut, Rolls-Royce's engineering divisions were in fact pursuing a formidable long-term solution, the pressure carburetor. This was no mere incremental improvement. It represented a fundamental leap in aviation fuel delivery technology. Unlike the conventional float-type carburetors, which relied on gravity and a delicate float mechanism susceptible to any deviation from level flight, the pressure carburetor was designed to positively inject fuel into the supercharger under constant pressure. This innovation promised numerous advantages: superior fuel atomization for more efficient combustion, consistent engine power output across varying altitudes and flight attitudes, and, critically, invulnerability to the very G-force anomalies that plagued the Merlin engine. It was the future of high-performance aero engines, offering a decisive technological edge over the Luftwaffe's direct injection systems already present in the Messerschmitt Bf 109.
Indeed, the development of such a sophisticated system was a strategic imperative, yet its very complexity was its immediate drawback. Engineering a robust, reliable pressure carburetor, integrating it seamlessly into the Merlin engine, and then scaling its production to equip thousands of Spitfires and Hurricanes was an undertaking measured in years, not weeks. Every component required rigorous testing, every design iteration refined through painstaking trials, and the retooling of manufacturing facilities represented a logistical bottleneck of immense proportions. While offering eventual technological supremacy and solving the G-cut permanently through a superior design, this long-term bet, for all its brilliance, provided no immediate succor to the pilots whose lives were being forfeit daily to the G-cut over the Channel. The pressing operational reality demanded a different kind of ingenuity, one capable of bypassing the protracted timelines of advanced development. The relentless attrition of RAF pilots, deuced by the inherent design flaw in the Rolls-Royce Merlin engine, created an untenable strategic situation. While the meticulous engineering teams at Rolls-Royce converged on the sophisticated pressure carburetor as the definitive, long-term solution, the brutal reality of air combat demanded an immediate, less complex intervention. Each day the pressure carburetor remained in development was another day Spitfire and Hurricane pilots faced the lethal vulnerability of fuel starvation during negative G maneuvers, ceding a critical tactical advantage to the Luftwaffe. The front lines of the air war could not await an elegant, multi-year engineering project. They required an ad hoc solution, one that was both swift to implement and economically viable for mass production. It was against this backdrop of urgent necessity and engineering orthodoxy that an almost astonishingly simple answer emerged, born not from the hallowed halls of Rolls-Royce's design bureaus, but from the keen observation of an individual often overlooked in the annals of wartime innovation. This was the Shilling orifice, a brass restrictor whose ingenuity lay precisely in its elegant simplicity. The core mechanism was disarmingly straightforward. A small, precisely bored brass washer, or restrictor, was inserted into the fuel line leading from the carburetor. Under normal flight conditions, this restrictor permitted sufficient fuel flow to the engine. However, when the aircraft executed a negative G maneuver,
pitching sharply downwards, causing the pilot to feel lighter in their seat. The restrictor's narrow aperture became crucial. It effectively limited the rate at which fuel could surge forward in the float chamber, preventing the momentary starvation that had previously plagued the Merlin engine. By dampening this sudden, uncontrolled rush of fuel, the restrictor ensured a continuous, albeit reduced, supply to the engine, thereby averting the catastrophic cutout. The very simplicity of this 50-cent solution, costing mere pennies to produce and minutes to install, was perhaps its greatest impediment to early recognition. Engineering culture, particularly in high-stakes wartime development, often gravitated towards complex problems, demanding equally complex and, consequently, expensive and time-consuming solutions. The idea that a fundamental design flaw, one costing lives and strategic advantage, could be mitigated by a mere brass washer seemed almost too rudimentary to be genuinely effective. Yet, this unassuming component would prove to be the stopgap that fundamentally reshaped the aerial balance of power. The skepticism surrounding Beatrice Shilling's brass washer was pervasive. Yet, the urgency of the attrition rates in the RAF's fighter squadrons demanded an immediate, albeit unconventional, validation. Formal channels, often mired and protracted testing protocols, were deemed too slow. Consequently, the first critical operational assessment of the Shilling orifice occurred with audacious informality. Air Commodore Sir Stanley Hooker, a pivotal figure at Rolls-Royce, recounted how test pilot Flight Lieutenant Davies, without official authorization, had the restrictor installed in his Hawker Hurricane. This unilateral action, bypassing the customary bureaucratic layers, underscored the desperate need for a rapid solution.
Davies' subsequent flight trials were meticulous, pushing the Hurricane through its full combat envelope, including repeated and aggressive negative G maneuvers that had previously proven fatal. His post-flight report was unequivocal. The engine performed flawlessly. The dreaded cutout, a phenomenon that had claimed numerous lives and crippled operational capabilities, had been definitively eliminated. This rapid, real-world validation, although technically unauthorized, provided irrefutable proof of concept. The simplicity of the fix, once its efficacy was demonstrated, became its greatest asset. The reverberations through the fighter command were instantaneous. Pilots, acutely aware of the mortal danger posed by the negative G issue, clamored for the modification. The Air Ministry, recognizing a tactical imperative that transcended engineering orthodoxy, swiftly granted approval for immediate, theater-wide deployment. The Shilling orifice, a component costing mere shillings to produce, was fast-tracked into mass production and retrofitted onto thousands of Merlin engines powering the Spitfire and Hurricane fleets. This logistical triumph saw an unprecedented acceleration in the adoption of a technical solution, driven by the stark realities of aerial combat. The impact was profound and immediate. Statistical data from operational squadrons revealed a dramatic and precipitous reduction in engine failures directly attributable to negative G maneuvers. Pilot casualties from this specific cause plummeted, instantly enhancing the operational readiness and morale of the RAF fighter arm. The German Luftwaffe's Messerschmitt Bf 109, which had enjoyed a distinct tactical advantage in dive recovery and evasion due to its fuel-injected engine's immunity to negative G issues, found its supremacy abruptly challenged. British pilots could now execute similar aggressive maneuvers without fear of fatal engine starvation, effectively leveling the aerial playing field. This unassuming brass component, conceived by an engineer who defied convention, demonstrably saved countless lives and provided the RAF with a critical, low-cost strategic equalizer at a pivotal moment in the air war. The story of the Shilling orifice transcends its immediate tactical impact, offering a profound insight into the very nature of the technical war waged across the European theater. It serves as a stark reminder that victory was not solely predicated on troop movements or strategic bombing campaigns, but on a relentless, often unsung, engineering contest. The initial flaw in the Merlin engine, exploited by the Luftwaffe's superior negative G maneuverability, presented a critical tactical vulnerability for the Royal Air Force. Rolls-Royce's pursuit of a sophisticated long-term solution, while technically sound, underscored the strategic dilemma of wartime innovation. Complexity often equated to delay, a luxury the RAF could ill afford with pilots perishing daily.
Conversely, Beatrice Shilling's deceptively simple brass washer epitomized another facet of wartime ingenuity, the elegant, immediate solution born from deep practical understanding and an unburdened perspective. This was not merely a fix, it was a decisive countermeasure that fundamentally altered the dynamics of close-quarters air combat, enabling Allied pilots to engage with newfound confidence and aggressive tactics. The incident underscored the enduring importance of adaptable problem-solving under extreme pressure, demonstrating that sometimes the most effective answers emerge from unconventional sources and challenge established engineering orthodoxies.
The legacy of this episode extends far beyond the immediate cessation of engine cutouts. It ingrained in aviation engineering principles the critical importance of considering the full envelope of operational conditions, including the often overlooked negative G scenarios. It validated the integration of field-level observations and practical, rapid prototyping into the design cycle. More broadly, it stands as a testament to the fact that in the crucible of conflict, ingenuity in all its forms, from the meticulous, long-term development of advanced systems to the swift, brilliant simplification of complex problems, is not merely an advantage but an absolute prerequisite for strategic success. The Shilling orifice remains a powerful narrative, a vignette of how a 50-cent component, conceived by an extraordinary engineer, became an invaluable weapon in the arsenal of freedom, forever shaping the trajectory of air warfare and its underlying technological ethos.